In the last few videos I showed how to use the YellowHat to set up a CTC panel, read buttons and set turnouts or signals. In this last part of the tutorial series I am going to combine these elements into one single application. The goal is to implement two CTC controlled yard sections with an ABS controlled track in between them. To add to the complexity, the ABS section also has a siding, therefore signal aspects depend on turnout positions as well. Welcome to the IoTT channel, I am Hans Tanner. The hardware setup for this tutorial is the same as before. A simple track layout with two terminal stations with two tracks each, and the middle section with two tracks as well. The track is split up in isolated sections or blocks equipped with current sensors for train detection. I also have transponding installed, but I am not using it for this example. As control system I am still using my old touch button hardware and a YellowHat to drive the picture frame CTC panel LEDs and run the event handler logic. Video 9 has more on how I built that CTC panel. For the signal mast I am using a blue hat that is driving the NeoPixel chain for the signals. If you want to see how I built the signals from scratch, watch video number 13. This slide shows the block section addresses and the turnout numbers. It also shows the installed push buttons that can be used to operate turnouts or activate routes or signals. The signals are placed to protect the turnouts, as it should be. They are controlled using DCC signal addresses, and this table shows the location and address of each signal. To keep things easy to memorize, I am using even numbers for eastbound signals and odd numbers for westbound masts. As in previous videos, I am operating the signals with three aspects: red for stop, yellow flashing for slow, and green for track speed. In videos 70 and 71, I controlled the track using a CTC approach, so I numbered the station tracks as shown here and defined routes to go from one station track to another. When activating a route, the turnouts were set accordingly, and when double-clicking a trigger button, the signals were set to allow for the train movement. Watch video number 71 to see this CTC system in operation. Now I am changing that concept to make the middle section an autonomous ABS zone with a siding. A concept that is found quite frequently in the prototype world as well as on model railroad layouts. The first thing to change is the route system, as the tracks in the ABS zone are no longer part of the CTC routes. For that purpose I introduce two new route terminal points labeled track 1 and track 2, which are located at the interfaces between CTC and ABS zones. CTC routes are now set from the terminal tracks to the interface section and vice versa, while the middle section has no routes. It is only possible to set the switches, and the ABS signals will change aspects accordingly. The result is a revised route table as shown here. We now have a total of 4 routes in each CTC section, going from the terminal tracks to the interface section and back. To activate the routes I am using the same mechanism as before, but I am only using button 171 in the middle section, as the ABS siding is no longer part of the route system. So to set route 100 eastbound from track 11 to track 1, I first press and hold button 171 and then click on button 178, and so on. Always first press and hold the destination button, then click the origin button, and button 171 serves as activator button for both CTC zones. To set the signals and trigger the train movement in the CTC zone, I am using the 4 buttons located next to the terminal tracks, but this time the function depends on the active route. If I double-click button 178 and the outgoing route from track 11 to track 1 is set, signal 802 is activated. In the other case, if the route from track 1 to track 11 is active, signal 811 is set, and so on. The signals in the ABS section are controlled by track occupancy, similar as shown in video number 69. only this time there is one more variable, which is the siding. Let's look at signal 804 for example. The aspect shown on this mast depends on the position of turnout 2, the occupancy statuses of blocks 0 or 60, the position of turnout 1, and finally the occupancy status of blocks 4 and 5. So for example, if turnout 2 is closed, the signal should show stop if block 0 is occupied, slow if turnout 1 is thrown or if it is closed, but blocks 4 or 5 are occupied, and track speed if turnout 1 is closed and blocks 4 and 5 are free. But then, if I change turnout 2 to thrown, suddenly the aspect needs to change according to the status of the other siding. That looks like a complex situation, and we certainly have to employ some magic hat tricks to implement it using a YellowHat. So let's get started with that ABS zone. When implementing ABS signaling, I find it best to always think about it from the perspective of the signal mast. As explained in video number 21, the purpose of a signal mast in a 3-aspect system is to protect the next 2 blocks in travel direction. Accordingly, it would be 3 blocks in travel direction in a 4-aspect signaling system, but that would make things considerably more complex, so I stay with a 3-aspect system. The signaling rules are simple and straightforward. If the block immediately following the signal is occupied, the signal shows red. If it is free, but the next following block is occupied, it shows slow, as the train needs to prepare to stop at the next signal. And if both blocks after the signal are free, the signal shows track speed. If there are turnouts in the upcoming blocks, the turnout position needs to be considered as well. If the signal is at the front end of the turnout position determines what next block to consider. Also, if the turnout is diverting, the speed settings must be lower than when it is set to straight. If the signal is at the rear end of the turnout, again the turnout position has an impact on the signal setting. If it is pointed to the other track, the signal needs to show stop, and the previous signal should show slow. Otherwise we can proceed, and the indicated aspect depends on the turnout position and the occupancy status of the next 2 blocks as usual. This table here shows what blocks and turnouts need to be considered to calculate the aspects of each ABS signal for my application. For example, signal 804's immediate block is 58 combined with block 0 or 60 depending on the turnout position, but never both at the same time. Furthermore, turnout 1 needs to be considered, as well as, depending on the position of turnout 1, the occupancy status of blocks 4 and 5, and so on. How can we set this up as a status machine in the event handler? Remember, the event handler has certain limitations. For example, it can only react on one kind of events at a time. For example, on block detector events, or switch events, or signal events, but not in mixed fashion. So if a signal mast depends on block occupancy and the turnout position to calculate the aspect, we have a problem. The other limitation is the number of input addresses that can be used in a single event handler. In most cases this is just 1, but for switches and block detectors it is up to 3, so we can create an event table that considers the statuses of up to 3 block detectors, but not more. The reason for this limit is that setup would become a nightmare. Just think about it. 3 binary inputs like block detectors result in 8 different status possibilities. Make it 4 addresses and it is 16, 32 with 5 addresses. So we would end up with truth tables larger than the setup screen. That's why I limit it to 3 addresses, but it means we have to find a workaround if we need more than that. And we need to find a way to deal with switch and block detector messages at the same time. The first technique I am using is changing everything to block detector inputs. So for each turnout I create an event handler that receives a switch command and sends out a block detector command. If a closed command is received, the event handler issues a block occupied message, and a block free message is sent in case of a thrown command. So whenever a change of the turnout position occurs, we get a notification in form of a block detector message that can easily be combined with the block detector messages from the current sensors. Look at the example of signal 804 here. We now get the information of the position of turnout 2 in form of block detector message 302. Depending on the status, we then can use the occupancy status of either block 0 if the turnout is straight, or block 60 if it is diverting. And then we still have the problem of adding the information from turnout 1 and the blocks following the turnout. That's weighs more than the 3 inputs we can process. The problem of selecting the correct immediate block is easy to solve by just defining 2 different event handlers, one for turnout 2 closed and one for turnout 2 thrown. So I define an event handler for block 302, which is the status of turnout 2, and give it as second address the block number of the block that is selected depending on the status. So for the first entry, this is block 0 and block 60 for the other leg. But wait, in both cases I also need to add block 58, which is the occupancy status of the turnout itself. So to do that, I create an event handler that combines block detector 58 and block detector 0 and returns a new block detector message on block 321, which is occupied as soon as any of the combined blocks is occupied. I do this because the granularity of detection is higher than what I need, so I need to combine detection sections together for the purpose of signaling. There are several situations like that, and here is the table of all the concentrators I am adding to reduce the number of inputs. So with this I can set the second block address to be evaluated for signal 804 to 321 in case the turnout is closed, and 322 if it is thrown. Remains the problem of the status of the following block, which in itself is a combination of several variables. But then we have a signal at the beginning of the block which displays an aspect that is the result of all these variables, and following the general rules for an ABS system, we know that signal 804 basically just shows an aspect one level higher than signals 806 or 808. For example, if turnout 2 is closed and signal 808 shows stop, signal 804 shows slow. If signal 808 is slow, signal 804 displays track speed, and if signal 808 already is track speed, 804 shows track speed as well. So in fact, the aspect shown on signal 808 determines whether signal 804 shows slow or track speed. But since 804 shows track speed as long as 808 does not show stop, we are down to 2 different statuses, which means we can substitute the signal aspect with a block detector message as well. So I create an event handler that generates a block detector message depending on the display of signal 808. If signal 808 shows stop, I send occupied. If it shows slow or track speed, I send free. And as shown in this table, I do the same for all the other ABS signals as well, plus the same for signals 810 and 811, which are CTC controlled, but the first controlled signals after the ABS zone, so they need to be considered for setting the last signal in the ABS zone. And with this little trick, we have it down to 3 block detector variables for signal 804. The first event handler reacts on input 302, which is the turnout position, 321, which is the combined status of block 0 and 58, and 308, which is the current aspect of signal 808. In the resulting truth table, I populate all entries that have input 302 occupied, meaning the closed position of turnout 2, and in the command list I set the aspect of signal 804 to either stop, slow or track speed depending on the status of the other 2 variables. The second event handler for signal 804 is similar, only here I use inputs 302, 322 and 306, which corresponds to blocks 58, 60 and signal 806. The setup of event handlers for signals 806 and 808 follows the same principle. Again, I am using three inputs. The first is the position of turnout 1. The second is the immediate block, which in this case is the same for both signals. And the third is the status of signal 810, which is the first CTC controlled signal, and again is the same in both cases. So very conveniently, I can use the same set of input addresses for both signals 806 and 808, so I can go with one single event handler for both. In the command list, I add one line for each signal. Signal 806, of course, is set to halt whenever the turnout is in closed position, and whenever it is thrown, signal 808 must show stop. The aspect of the other signal depends on the status of the immediate block and the aspect shown on signal 810 and can be stop, slow or track speed as usual. So with three event handlers I can control the eastbound signals, and all I have to do now is copy them and change the addresses, and I can control the westbound signals as well. So a total of 6 event handlers plus some to substitute turnout positions and signal aspects by input messages, and the YellowHat can handle the entire ABS zone including the siding, and no computer is needed. Now that the ABS zone is working, the only remaining thing is the routes and signals for the CTC sections. I basically used the settings from video number 71 and just shorten the routes and remove the now ABS controlled signals from the routes. Since the basic setup of the routes is the same as shown in video number 71, I do not explain the details here, but as with the other tutorials, you can download the data files from the GitHub page listed below. Here is the list of the event handlers used to make the example work. With this list, it is easy for you to load it into your IoTT stick, open the event handler tab and try it for yourself. So let's move on and test the system, starting with the ABS zone. First, let's have a look at signal 804 going eastbound. Switch 2 is set to closed and the immediate block is empty. Signal 808 is showing stop because switch 1 is set to thrown, and therefore signal 804 shows a yellow flashlight indicating slow. In the distance we see signal 810 showing slow to allow a train entering the terminal track 21. I now change the position of turnout 1 from thrown to closed, which causes signal 808 to change from stop to track speed, and as a result signal 804 is changing to track speed as well. Signal 806 on the other hand changes to stop as the track temporarily became a dead end. Now I change signal 810 to halt, and as a result signal 808 changes to slow. Signal 804 remains on track speed as there is no need for the train to slow down in the first part of the ABS zone. Next, I move a train into the ABS section. As soon as I enter, signal 804 turns red because the immediate block is now occupied. Signal 808 still shows slow, but changes to red if I change the position of turnout 1. Instead, signal 806 changes from stop to slow. Note that it does not change to track speed as turnout 1 is thrown and therefore the allowed speed is limited. If I now change turnout 2 to thrown, signal 804 changes from stop to slow. As the immediate section is free, therefore a train can enter into the siding, but with limited speed as it is the diverting track. I change turnout 1 back to closed and activate the incoming route to track 21. Turnout 0 is set to closed and the control signal 810 is set to slow as soon as I trigger the train movement with a double click on button 179. As a result, signal 808 changes to track speed. I move the train to track 21 and the route is automatically cleared by the CTC area and signal 810 is set back to stop. If I move a train in the other direction from track 21 through the siding towards track 11, I can see the opposing signals changing from track speed to slow to stop as the train approaches, and then going back to the higher aspect once the train has passed. Just as expected, so it appears the ABS zone is working as intended. Finally, a quick test of the CTC zone, even though this is the same functionality as used in video number 71. With a train sitting on track 12, I set a route to exit the CTC area and move towards the ABS zone. I hold button 171 as destination and click button 175 to select the origin. Switch 3 is changed to thrown and the track indicator LED shows that the route is set. I now double click button 175 and the aspect of exit signal 800 changes to slow. When the train starts to move, the occupancy LEDs on the panel are updated accordingly. Once the train has left the CTC zone, the route is cleared and the signal set back to stop. Handling an incoming train works the same way. I first hold the destination button of the track I want to move to, in this case 178 for track 11, then click the origin button 171. The route is set and as soon as I double click button 178, the yard entry signal 811 is set to slow and the first ABS signal 809 in this example goes to track speed. The train then moves into track 11 and the route is cleared, signal 811 put back to stop and 809 changes to slow as it is part of the ABS zone. So that works as well and we can summarize what we have done. As seen before, a CTC panel is a status machine that turns events like sensor inputs and button inputs into action using the if this then that model. Both types of signaling systems, ABS and CTC, can be modeled using this status machine approach and therefore they can be implemented using the event handler of the IoTT stick. To support ABS signaling, generally one event handler per mast is needed to protect the next two blocks in travel direction. Depending on the complexity of the track layout, the number of inputs may have to be reduced. Typical techniques to do so are substitution and concentration. Overall, the event handler of the IoTT stick proves to be a simple and flexible tool to do some layout automation tasks without having to use a computer. And that's it for today. I hope this information was useful or at least interesting for you, and you have a better idea about what the event handler of the IoTT stick can do to implement signaling on your model railroad layout. If so, please click the like button below and leave a comment in the comment section to let me know. And if you want to experiment with that setup for yourself, you can download the event handler and LED chain setup data used in this example from the config data section of my GitHub page and load it into your IoTT stick. Thanks for watching and see you in the next video.